Thank you very much for the nice introduction. It's really a pleasure to be here. I would like to talk about a result I discovered, a result on matrices. It was a very elementary result, and I was very excited about it because it's not so easy to find new elementary results about matrices. And unfortunately, it turned out not to be a new result. It turned out to be equivalent with von Neumann's theorem, so now my talk is not a new result on matrices, but a new proof of von Neumann's theorem. Von Neumann's famous theorem in game theory. But I'll explain everything, and everything I explain will be very elementary. I will assume that you only know what induction is, what linear combinations and things like that are. So very elementary, a very elementary proof. Let me first state the result which I'm going to begin with. It's a min-max result for real matrices. So we consider a real matrix A. The numbers AI, J are real numbers. The rows will be numbered R1, R2 up to Rm. So it's an M by N matrix. The column vectors are C1, C2 up to Cn. And then I'm going to look at convex combinations. So let me define what a convex combination is, although you know it. We take a linear combination of the rows, and all the coefficients should be between 0 and 1, and they should add up to 1. So this is what we call a convex combination. We also take a convex combination of the columns. And when I talk about a row vector, I mean one of these, but I also mean, I will also call this a row vector, although this is slight abuse of notation. So a convex combination of rows, I will also call that a row vector. And then let us look at such a row vector R. It has a smallest entry, it has a biggest entry. Let's take the interval between those two entries. I call that the row interval corresponding to this row vector R. So it's the smallest real interval which contains all the entries. That's a row interval. And of course a column interval we define in the same way. And then I would like to mention an observation, and in the following I'm going to refer to it, and I'm going to call it the trivial lemma. And it's the following. It's actually a rather nice thing. If you take a row interval and if you take a column interval, then they'll have something in common. This is not obvious, because if you take two row intervals, they need not have something in common. If you take two column intervals, they need not have something in common. It's very easy to give examples of that. But if you take a row interval and you take a column interval, then they do have something in common. And the proof is easy. Therefore, I call it the trivial lemma. Just look at this double sum here. So here you have the coefficients, the entries in the matrix, and here are the coefficients which you used when you formed the row interval, and here the coefficients for the column interval. So let's look at this double sum. And let's write it in this way. Let's first take the summation over the x's, and then, so we make the summation over the row elements here, and then later the column elements. Now let's look at what you have here. The x's were used when you formed the row vector. So you had a convex combination. You had a convex combination of the row vectors, and if you look at this number, that's precisely the jth coordinate. That's the jth coordinate of the row vector. And therefore what you have here, this big sum, that's a convex combination of elements in the row interval. But an interval is a convex set. If you take a convex combination over elements in an interval, you will stay inside that interval. And therefore, so you see, this is a convex combination because the sum of these y's is 1. So therefore, you stay in this row interval. But you can, by exactly the same argument, by making the sum in the other order, you can conclude that this number, this particular number, is also in the column interval. So I have pointed at a number which belongs both to the row interval and the column interval. And the proof is absolutely trivial. So now I'm going to do something with this row interval. And I'll explain the theorem with a little diagram. So look what you're doing here. You look at all the row intervals, and then you try to push the maximum as low down as possible. So the row interval has a maximum, and you select the convex combination in such a way that this maximum is smallest possible. So you push this as much as you can to the left. And you do the same with the column interval, except that now you focus on the left end point of the interval, and you try to push that as far as you can to the right. I mean, if you take the row interval and the column interval, we know that they intersect. So in general, they will look like this. But now we push this one as far to the left as possible, and we push this one as far to the right as possible, and then something very nice happens. Then these two numbers become the same. They become the same. And this number, this common number, when you make these two the same, that can only happen in one way, because any row interval intersects any column interval. So it's not possible to do it in two different ways. Then you will get a contradiction with this trivial lemma up here. So the number you get here is unique. And I call that the rendezvous number of the matrix. So this is a definition of a number associated with a matrix. And when I discovered this, I was, as I said, very excited, because I thought this was a new number associated with a matrix. And now you have all sorts of questions. What does this number mean about the matrix? If you have a symmetric matrix, it becomes particularly nice, because if you have a symmetric matrix, then rows and columns are the same. So this means that any two rows also intersect, and any two columns intersect. I'm going to give a proof of this, because the proof is very short, and then I will point out that this is in fact equivalent to von Neumann's famous theorem in game theory. So the proof is by induction on the size of the matrix. This is the number of entries in the matrix, and we do induction on that number. It's very easy to prove it if you only have one column, or if you only have one row. If you think about it for a few seconds, you'll see that this is easy. So I'm not going to go through that trivial case. I will assume now that the number of columns is at least 2, and the number of rows is at least 2. And then I'm going to prove this statement by induction. So let me repeat what I'm trying to prove. I'm trying to find a column interval and a row interval such that they meet in just one point. Remember how alpha was defined. That was when you took a row interval and pushed the right end point as much as possible to the left as you could. So let's look at the row vector which realizes this alpha. So alpha is the biggest number in this row vector, and I will assume that alpha appears on the first entry, the second entry, and up to the qth entry. If this does not happen, I mean, this occurrence of alpha could of course be many other places. Then I would just commute the columns. And it turns out that if you commute columns, that does not change the problem. So let me assume that I have a row vector which consists of alphas here, and then something here which is strictly smaller than alpha. Now I'm going to look at two cases. I'm going to look at the case where there is nothing here. That will be the second case, and the first case is when there is something here. So this means that Q is strictly smaller than N, because then I can do induction. So this is the case I'm looking at. My row vector which realizes alpha has some occurrences of alpha, and then there are some entries, some elements in the vector which are strictly smaller than alpha. And the number here, the coordinate here, I call Q. And now I look at the first Q columns in the matrix, and I'm going to use induction on that submatrix. I call that submatrix A prime. And let me use the induction hypothesis and see what we get. So The induction hypothesis tells me that I can find a row vector just using these smaller rows, and I can find a column vector just using these columns. They are also columns in the original matrix. These rows are not rows in the original matrix, they are smaller. But I can find such a row vector and I can find such a column vector such that their corresponding intervals look like this. They are like this. I mean, the biggest entry here, I call that alpha prime. That's equal to the smallest entry here, which, what do I call that? Do I call that something? No, there's no need to, because that's alpha prime by the induction hypothesis. And since I'm using smaller rows here than in the original matrix, this alpha prime will be smaller than or equal to alpha. I mean, when I realize my alpha, I can look at the smaller vector corresponding to these columns, and that will give me a smaller, largest coordinate. So alpha prime will be smaller than or equal to alpha. That's easy to see. So let's look at the case when alpha prime is equal to alpha. Well, in that case, we have finished. In that case, we are finished, because we do have our row interval coming from this vector up there. And if that stops here, I have another column interval, which also stops there. And then we have proved the theorem. Then we have the two intervals I want. So we only have trouble if this alpha prime is strictly smaller than alpha. So that's the case I'm now going to look at. And it will only be this one transparency, then we have finished. So I repeat, we have this row vector from the smaller matrix. We have this column vector also from the smaller matrix, but these columns are also columns in the original matrix, and the corresponding intervals look like this. The biggest end point here is the smallest end point here. So they look like that. Then I also have my row vector to begin with, the one which realizes alpha. And alpha is strictly greater than alpha prime, we assumed, because if it wasn't, we had finished. So let's see what we can get out of these three intervals. And this is just repetition. Well, I'm now going to look at these original rows. But now I will not use these coefficients. No, I will take those coefficients up there and see what we get out of that. So the rows in the big matrix, in the original matrix, but now I use the coefficients which I used in the reduced matrix. Let's see what we get. Well, we know what we get on the first q coordinates, because what happens up there, we can control that, and all the entries here are smaller than or equal to alpha prime, and alpha prime is strictly smaller than alpha. So what we have here is strictly smaller than alpha. What do we have here? I have absolutely no idea. This we cannot control. These could be very big numbers which we cannot control. Therefore, we do the following. I now form a convex combination of this one, this new vector, and the original vector r. So what we have here is a convex combination of those two. And since this one is a convex combination of rows and this one is a convex combination of rows, then when I take a convex combination of convex combinations, I still have a convex combination. So this is a convex combination. That's okay. And let's see what we get. Well, look here. We have something which is strictly smaller than alpha. And here we have equal to alpha. Therefore, what we have here is strictly smaller than alpha. If you take a convex combination of some alphas and some which are strictly smaller, then you get something which is strictly smaller. Provided, of course, that these coefficients z and 1 minus z are different from 0. I'm going to assume that. So here I have something which is strictly smaller than alpha. But look what I have here. Here I have something which is strictly smaller than alpha. And here I have question marks. But where I have question marks, I now choose a very small number close to 0. So those question marks will not give me trouble. By choosing Z very, very small, I can make this vector arbitrarily small here. And what about this one on these entries? Well, that's by birth strictly smaller than alpha. And this means that these are strictly smaller than alpha. So see what I've gotten. These are strictly smaller than alpha, and these are strictly smaller than alpha. But that contradicts the definition of alpha. And that finishes it. So here's what I did. When Z is small, all coordinates are strictly smaller than alpha, and that is a contradiction to the definition of alpha, because alpha is defined as the smallest thing I can get. And now I have something strictly smaller. Well, that was in the case when, do you remember, when Q was smaller than N? I mean, when we have something here, this means that this length is strictly smaller than this length. Otherwise, I could not use induction. So I still have to look at the case when this one continues to the end here. Then my proof will not work because I cannot do induction. But this means I have a constant vector. This means that my row vector is constant. So that's the second case. The row vector is constant. What do I do here? It just consists of alphas. Well, by transposing the matrix, I can assume that my column vector is also a constant, beta. So I have a constant vector here, and I have a constant vector here. What do I do in that case? Well, I just use the trivial lemma. Because what is the row interval here? That just consists of alpha. What is the column interval here? That just consists of beta. And I proved that any row interval and any column interval intersect, but then these two numbers are the same, and the proof is finished. So this is a very useful thing about matrices. And now let me convince you that this implies von Neumann's min-max theorem. And of course, I'll explain completely what this theorem says. So here is one way to explain this theorem. Let us look at a two-person game. We have two players. Player 1, who has a dice, number 1. I call it a dice, I mean, a thing like this. I think if you speak correct English, it should be a die. Is that true? Yes. But I hope you will forgive me for calling it a dice, because I can't get used to the other thing. So I say one dice and two dice. So player 1 has a dice, which we call number 1. Player 2 has a dice, which we call number 2. They both throw this, and suppose dice number 1 shows 2 and dice number 2 shows 3. Then player 1 has to pay some money to player 2. And that's given by a matrix. I mean, 2, 3, there is a number, A2, 3, telling us how much player 1 has to pay to player 2. It's always player 1 who pays to player 2. But of course, these numbers could be negative. So money could go the other way around. So we have a 6 by 6 matrix which tells you how much player 1 is going to pay to player 2 every time. This matrix has a name. It's called the payoff matrix. And it's not hard to see how much player 1, we repeat this very often, and how much must player 1 pay to player 2? Well, if you get eyes on dice number 1 and eyes on dice number 2, you pay this number, and then you just take the average of this number. So that's the expected payment. So that's not so interesting. We know exactly what happens. But now we are going to make it interesting. Now we will allow player 1 to cheat. He is allowed to change his dice. So if you look at the dice, he can change the dice so that the probability for eyes on dice number 1 will be this number, and he can choose that as he wishes. There's only one condition. He has to tell it to player 2. And then player 2 is, of course, also allowed to cheat. So what player 2 will do now is find a number between 0 and 1, which is the probability for j eyes on dice number 2. Let's take an example. Suppose this is the payoff matrix. Player number 1 is very unhappy here because all the numbers are positive. So this means that he has to pay every time. And there's no way around this. But player 1 is now allowed to cheat. And then he looks at this number 0. He likes that number 0. And in order to get 0, he has to throw 2. His dice has to show, we have to be in the second row here. And also there are all these 1s. So he may do the following. He may say that the probability that his dice will show 2 is 1. So it can only show 2. And he puts all the other xi's equal to 0. All these numbers have to add up to 1, and they have to be between 0 and 1. But that was not wise, because he has to tell player 2 what he has done, and then player 2 will notice this number 7. And then, of course, he will make his dice so that he can only throw 5. And this means that every time player 1 has to pay $7 or whatever to player 2. So that was not a good idea. That was a very bad move of player number 1. So what should player 1 do? We are going to assume that both players play optimally. So what would you think? Is it best to be number 1 or is it best to be number 2? Does it depend on the matrix? So let's say that player 1 cheats first and player 2 cheats next. And let's say that the average payment is alpha. There will be an average payment once those probabilities have been decided. Then let's next assume that we let player 2 cheat first, and then player 1 cheats next, and then the average payment will be beta. So what do you think is biggest? Well, von Neumann's famous theorem says that it doesn't matter. It doesn't matter who cheats first. The outcome will be the same. Provided, of course, that both play optimally. And I'm going to prove this now using this little thing about matrices. So here is the proof, and it's just one transparency. So let us suppose that player 1 chooses these numbers. Then player 2 chooses these probabilities. And since probabilities are numbers between 0 and 1, and they add up to 1, we can think of them as coefficient in convex combinations. And we're going to do that. We're going to look at the average payment. What is that? Well, the probability that there will be i's on dice number 1 and i's on dice number 2 is this product. And here is the payment. And therefore, this sum is the expected payment. And we will now write it in this form as we did before. Now, the x's come first. So once the x's have been established, player 2 will look at this number here. What is this number? Well, that's the jth entry in a convex combination of the row vectors, where the coefficients are the probabilities given by player number 1, the jth coordinate. And what is it player 2 wants to do? Well, of course, he wants to maximize this number. So he just looks at this vector. He just looks at this vector and takes the biggest number. That's the best for him. So player 2 maximizes. So this means that he puts yj equal to 1 corresponding to the largest number in the row interval. He takes the largest number in the row interval. But player 1 knows that. Player 1 knows that. So therefore, of course, he chooses these so that he minimizes that largest number. So maybe you remember the first picture. Let me remind you of the first picture. So here is the row interval. And player 2 chooses the biggest element in the row interval. And player 1 knows that, and therefore he will push that number as low down as possible so that he can pay as little as possible to player 2. And this means that we get the rendezvous number of the matrix. And by exactly the same argument, if player 2 starts cheating and player 1 is the second, then we'll focus on this beta. But since when we push this down as far as possible and this up as possible, we get the same number. So it's the same number in both cases. So that's for Neumann's min-max theorem in game theory. Why is it called a min-max theorem? Well, because if you have a given matrix, then you can look at this expression where the xi's and the yj's are convex combinations, coefficients of convex combination or probability distributions. And if you have maximum here and minimum here, you can reverse them and you get the same. I mean, in general, if you have a function of two variables and you maximize with respect to one variable and minimize with respect to the other variable, then usually the order in which you do this is very important. I mean, you can make easy examples showing that this is very important, but for this special case, it doesn't matter. Now, rendezvous numbers. What has that to do with for Neumann's min-max theorem? Let's consider a metric space M. Just any metric space, and here is the metric. That's the distant function. And if you don't want to think about a general metric space, you can just think of a subset of the plane, for example. That will be sufficiently interesting. Now let's take a positive number, alpha. We will say that this is the rendezvous number of this metric space if the following is satisfied. So this little picture will show it. Here comes the definition of a rendezvous number. Some people call it a magic number for a metric space. It's a magic number or a rendezvous number if the following is satisfied. Whenever you take a sequence, well, a collection of points in the metric space, and it could be any number. It could be just 1 point, it could be 2 points, it could be 1,000 points, and they don't have to be distinct. There could be a lot of repetition. Whenever you do that, it should be possible to find an element in the metric space such that the average distance from this element to all these points is equal to alpha. So if you look at this expression, this is the distance from Q, from this point to pi, then you take the summation of all these and divide by n, that's the average distance. And that average distance should be precisely alpha. So you might say it might be difficult to find such a number alpha, and what is it? For example, on this campus of KAIST, there will be a rendezvous number. What is the rendezvous number? Well, first we should ask, is there a rendezvous number? So whenever some people on the campus want to meet, you want to find a neutral place, namely a place such that the average distance to that place is always the same, so that no groups are favored to other groups. Whenever a group has to meet, the average distance to that point will be alpha. So the meeting point could be different, but the average distance will always be the same. It sounds as a remarkable property that such a number should exist, but it does. Here is a beautiful theorem of Gross, namely that if you take a compact and connected metric space, it has precisely one rendezvous number. So this campus, provided it's connected, and I believe it is, well, I don't know if there are branches at other places, but suppose it is connected, then this campus has precisely one rendezvous number. But I don't know what it is. I should say what connected means. Well, this means connected in the topological sense, but if you don't want to think of that definition, you could think of arcwise connected. So this means that between any 2 points, you can find a curve, a continuous curve connecting them. And compact, well, that's a standard topological definition. If you just want to think of the plane, compact means, as you know, the same as bounded and closed. It's important that we have boundedness. That's clear, because if you want the average distance always to be the same, and if you have an unbounded space, that is not possible. because if the space is unbounded, you can find 2 points of distance at least 1. The average distance will be at least a half. Then you can find 2 other points of distance at least 2. The average distance will be at least 2, and you can go on, and you'll see that there will not be such a number if it's unbounded. But if it's bounded, and closed, if we are talking about the plane, and then connected, then there is such a rendezvous number, and there is only one. So there are two things in this. There is an existence part, and there is a uniqueness part. And it turns out that the existence part is the easiest one. I mean, to me it sounds, the first time you hear this, the existence part sounds a little dramatic, unbelievable, but it's actually the uniqueness part which is the most difficult. And I'm going to prove this by a simple argument. Maybe we should take an example to get used to this concept. Let's try to find the rendezvous number just of the unit interval. Let's see what the rendezvous number is. Well, you might take these 2 points P1 and T2. And then if you take any third point Q, the average distance to these 2 points will be a half. So this means that if there is a rendezvous number, there is only one possibility, namely a half. It's the only possibility. I mean, just by looking at these 2 points. I mean, if these are the 2 points you want to go to, and you want to find a common meeting point, what is the average distance from that meeting point to 0 and 1? Well, the average distance is a half. So that's the only possibility. But now I'm going to prove that a half is really the rendezvous number of this interval here. And this little argument I'll use in the following also. So let me take n points P1, P2 up to Pn in this interval between 0 and 1. And let me prove that I can find a point Q whose average distance to these is precisely a half. Let me first try with Q equal to 0. Then the average distance is this. And I have no idea what it is. It might be close to 1, it might be close to 0. I can't tell. Then I also try Q equal to 1 and look at the average distance from 1 to these points, and again I cannot control this. I don't know what it is. But I can look at those two average distances and add them together. And if I do that, you'll see it becomes very easy, because this number here plus this number is equal to 1. So when you add all these things together and divide by n, you just get 1. But this means that if this one here is smaller than a half, if this one is smaller than a half, then this one must be bigger than a half. Okay, but now I start letting Q be 0, and I move Q slowly, continuously from 0 to 1. At the beginning, the average distance is smaller than a half by this inequality, and at the end it's greater than a half. So somewhere in the middle, it must, well, not in the middle, but somewhere in between, it must be precisely a half by continuity, because this metric function is a continuous function. And you know, if you have a continuous function which is negative at some place and positive at some place, there must be some place. What is that called? Is it Roller's theorem or something like that? Well, this is high school stuff. So we must get a half as a rendezvous number. We can generalize this a little bit. So here are just some simple observations on rendezvous numbers. As usual, when we have a metric space, we define and it's compact, we define the diameter as the maximum distance. In general, I ought to write supremum here, but if it's compact, then this supremum will be attained, and I can just work with a maximum here. If you have a point P, you can look at the maximum distance from T to other points. That's called the eccentricity of that point. And if you minimize that eccentricity, you get what we call the radius. Maybe I should have written these things here. So this number is radius. So every compact metric space has a diameter and it has a radius. And it's clear that the diameter is greater than or equal to the radius, because the diameter is the maximum distance and the radius is some distance. As you can see, the radius is some distance, and therefore it's smaller than the maximum distance. But it's also easy to see that the diameter is at most 2 times the radius. Because when you realize this eccentricity, we could call that the center of the metric space. And if you take 2 points in the metric space and look at the distances to the center and add them together, then the triangle inequality will give you that the distance between those 2 points is at most 2 times the radius. Well, if you have a metric space where the diameter is equal to 2 times the radius, as for example the unit interval or a circle in, not a circle, but a disk in the plane, or many others, many convex sets have this property, then it's easy to find the rendezvous number, because the rendezvous number is just the radius. And the argument is, it's easy, because if you look at these 2 points and you try to find a meeting point Q, what is the average distance from a point here to these two? Well, it's at least half the diameter. So the average distance from this red point to P1 and PQ is at least half the diameter. You could also look at the center. Put a point P1 in the center and look at another point Q. What is the average distance from Q to this point? Well, that's just the same as the distance from Q to this point. Well, that's at most the radius. And this means that the rendezvous number must necessarily be at most the radius. So if it's at least half the diameter, in general it's at most the radius, and if these two numbers are equal, we know the rendezvous number. So that's easy. But there are many metric spaces where you don't have this, where you don't have this equality. And for those spaces, the rendezvous number is interesting. I would like to drop connectedness. I would like just to look at a compact metric space. If you just have a compact metric space, it need not have a rendezvous number, because if you take the metric space just consisting of 2 points, if you think about it for a minute, you'll see that that space has no rendezvous number. But it turns out that it has another number, what I call a weak rendezvous number, and the definition comes here. So we will say that alpha is a weak rendezvous number of a metric space if for any collection of points, P1 up to Pn, you can find, now you find 2 points instead of just 1 point. So 1 point Q, another point Q prime, such that the average distance to Q is at least alpha, and the average distance of these points here to Q prime is at most alpha. So you can get an average distance at least alpha and an average distance at most alpha. And then we get the following theorem. Every compact metric space has precisely one weak rendezvous number. So again, we have existence and uniqueness. Precisely one weak rendezvous number. And I would like to indicate the proof of this. The proof is not long. Let me first look at the interesting case when our metric space is finite. Let's assume that the elements are T1, T2, etc. And let me show what the weak rendezvous number is. Let's look at the distance matrix. You have finitely many points, and we look at all the distances, and we can write them as a matrix. And of course, that's a symmetric matrix. And let alpha be the rendezvous number of this symmetric matrix. Then it turns out that this alpha actually works. And let me explain why it works. So we have this matrix, the distance matrix A, and its rendezvous number is alpha. And I'm now going to prove that alpha is a weak rendezvous number of the metric space. So what are we going to do? Well, we are going to take some elements in the metric space, and we may have repetition. We may have repetition here. When we have such a collection of elements, we can also think of that as a probability distribution on the elements of the metric space. And when we have a probability distribution on the elements of the metric space, this means that there is a probability associated with every element. We can also think that as a convex combination, because we can use those numbers as coefficients when we make convex combinations. So that gives convex combination of the rows in the distance matrix of A. I don't know if this is clear, so let me give an example. So again, we start with some points and we are going to find a meeting point. Rendezvous means meeting. Let us assume that P1 is, for example, the second element in the metric space, and let's assume that P2 and P3 are both the fourth element in the metric space. What do I mean by probability distribution when I have selected these three elements? Well, I'm going to say that the probability of this element is 1 over 3, because it occurs 1 out of 3 times, and the probability of this element is 2 over 3, because it appears 2 out of 3 times, and all other elements have probability 0. That gives us a probability distribution, but when I have that, I can also use those numbers as coefficients in a convex combination, and I'm going to do that. Then it turns out that the ith coordinate in this convex combination, I mean, this is again trivial. If you think of the ith coordinate in this convex combination, so you take the ith column, that turns out to be the average distance from Ti, from this vertex, from this element Ti to these selected points. So when you form this convex combination, you get what I called a row interval. We know that this row interval contains alpha. It contains alpha. But if you have a row interval containing alpha, then some entry must be bigger than alpha and another entry must be smaller than alpha. I mean, some entry here must be bigger than alpha and some other entry must be smaller than alpha. But this means that this number alpha is a weak rendezvous number if you go back to the definition. And in this way we have proved the existence of a weak rendezvous number. And similar arguments also show the uniqueness. So I'm not going to say more about uniqueness. Let me just mention how you do it in the infinite case. If you have a metric space which is not finite, and what I'm saying now may not be completely transparent, so this is just a sketch of what is going on. I don't expect you to follow the details, but if we have an infinite metric space which is still compact, then I'm going to prove that the alpha, sorry. I'm going to prove that there exists a weak rendezvous number. I'm going to point it out, and I'll just point it out, and I'll leave the proof out that it's really the weak rendezvous number. But we need a method to point it out. So what I do is, I will now look at a vector consisting of points in the metric space. It could have any length, and there could be a lot of repetition. I'm also going to look at a convex combination. Well, I'm going to look at you could say, probability distribution on these points. So this means it's just it's just a vector of the same length of this, and all the elements are numbers between 0 and 1, and they add up to 1. So I take any such sequence, and I take any such sequence here, and then I define this interval as the smallest interval which will contain all these numbers. You remember we have seen these numbers before. So this is the smallest interval containing all numbers of this type. Now an important thing. If you take this interval and you take another interval formed by the same method, but of course with different p's and with different x's, then what happens? Well, it turns out that those two intervals have something in common. And how do we prove this? Well, I don't expect you to follow the details, but it turns out that you just use the trivial lemma to the distance matrix of all these points. So I take the original points and I also take the new points. And as I said repetition is allowed. There may be a lot of repetitions here. It doesn't matter. So we have a situation where we have a collection of intervals and any two of them intersect. And now a special case of Helly's theorem says that if you have a collection of intervals on the real line, any two of them intersect, then they all intersect. And if you think of it for a few seconds, then any alpha, any number alpha, which belongs to the intersection of all those intervals will satisfy the requirement of the weak rendezvous number. It's just a matter of checking the definition. It'll take a few seconds, but there's nothing difficult in it. Then I'm going to skip the proof that there cannot be more than one rendezvous number. It only takes one transparency, but I think I'll skip it. And let me do something which is slightly more general. I still have a little time left. So now let's drop compactness. I mean, so far, first we had compact connected spaces. Then I dropped connectedness and say, let's look at compact spaces. Now I say, let's just look at bounded spaces. This means that the diameter is smaller than infinite. So it means that there exists a number such that all distances in the metric space is smaller than that number. A bounded metric space. But not necessarily compact anymore. What can be said in this case? Well, it turns out that this space need not have a rendezvous number. It need not even have a weak rendezvous number. And to see that, you just consider the open interval between 0 and 1. That has no weak rendezvous number. The only candidate for a weak rendezvous number would be a half, but that doesn't work here, as you can quickly see. But it turns out that it has what I call a very weak rendezvous number. So here is, I think this is a natural definition. So now you look at any collection of points and you want to find a meeting point, but you also allow a small number epsilon, and then you should be able to find 2 points, q and q prime, such that the average distance to q of these points is smaller than alpha. Greater than alpha. But now I make it a little more flexible, so I say greater than alpha minus epsilon. And the average distance to q prime should be smaller than alpha plus this little number epsilon. So I just allow a little flexibility with an epsilon. Otherwise, it's the same as the weak rendezvous number. Every such metric space has a weak rendezvous number. And again, it's just a repetition of the trivial lemma. You just have to keep track of more things. But now we don't have uniqueness. I mean, when I spoke about weak rendezvous numbers for a compact metric space, it's unique. So uniqueness is rather surprising. Here we lose uniqueness. And let me just explain why we lose uniqueness. And since I'm a graph theorist, I think I should at least have one transparency showing at least one graph. And I'm going to show a big graph now, the so-called universal graph. It's a countably infinite graph, and it's the following thing. You start with a vertex. G1 is the graph just consisting of one vertex. And then you construct, from G1 you construct G2, you construct G3, etc. And assume that we have constructed Gn, then I'll explain to you how we construct Gn plus 1. You do the following. Here we have Gn, and you take any set of vertices. You take any set of vertices and you add a new vertex and join it to precisely those vertices. You do it for every subset of vertices. So you do it for the subset I have shown, but you also take this subset and do the same thing, and you take this subset and do the same thing, and then you get Gn plus 1 when you have done that. So when you go from Gn to Gn minus 1, that's a big expansion. And then when you have done it for all natural numbers, you just take the union of all those graphs, or the limit if you want to explain it that way. So that's a very interesting graph. It's the universal graph. It has the property that any finite graph can be found as a subgraph in this graph, as what we call an induced subgraph in this graph. So it has many other nice properties. And if you take an infinite collection of points, a countable collection of points, and for every pair you toss a coin and let that decide if the edge should be there or not be there. That's called the infinite random graph. The infinite random graph. I mean, we sometimes talk about a random graph, and this is a very general concept which in some sense says something about a lot of graphs. But in the infinite case, there is only one random graph. We always get this one when you toss a coin for every possibility of an edge. But also in this connection, it's interesting because it's a metric space where there are only two distances. So we look at the metric space as being defined on the vertices. And when you have two vertices, you can look at the edges in the shortest path between the number of edges in the shortest path. That's called the length. So every graph gives rise to a metric space defined on the vertex set. And all distances here are 1 or 2. All distances are 1 or 2. Because, look, if you have two vertices, they may be joined by an edge, and then they have distance 1. If they are not joined by an edge, they will belong to some gn. And they are not joined by an edge, but then there will be a vertex joined to both of them, because when we go from gn to gn minus 1, any vertices here will be adjacent to one of the new vertices. So all distances are either 1 or 2. And if you think about it for a little while, then you will see that every alpha in this interval is a very weak rendezvous number. So the very weak rendezvous number, there is no rendezvous number. But there are many. Is there a weak rendezvous number? No, I don't think so. There's no weak rendezvous number, but there are very weak rendezvous numbers. And every number between 0 and 1 will satisfy the definition. So you see, we have existence, but we don't have uniqueness. And then let me finish with an unsolved problem. At least it was unsolved in 1986 when it was made, and I believe it's still unsolved. I've not seen the solution to this. Let us look at compact connected subsets of the plane. And let's say that they have diameter 1. I mean, if you have such a set in the plane, you can scale it down so that the diameter is precisely 1. Let's look at such a thing here. And let's ask, what can the rendezvous number be? Well, you know, if the rendezvous number will be at least a half. And if the radius multiplied by 2 is equal to the diameter, then the rendezvous number is equal to a half. So that is not so interesting. But we can ask instead, what is the maximum rendezvous number for such a thing? I mean, the minimum rendezvous number is a half. That's easy. But what is the maximum? We don't know. But there is a conjecture that the maximum is obtained from the so-called Rouleau triangle. So the Rouleau triangle consists of 3 circle segments. So what you have here, it's part of a circle whose center is this, and the radius is 1. So what you have here is part of a circle of radius 1 and center here. And similar with this one. This is part of a circle with radius 1 and center here. And similar with this one. Now, if you put a point P1 here, and a P2 here, and a P3 here, then you will see that the average distance to these 3 corners is at least 2/3. At least 2/3. But if you instead put many, for example, 100 points here, 100 points here, 100 points here, and just 1 point here, 1 point here, and 1 point here, the average distance becomes a little more than 2/3. And one can actually push it up to more than this. One can push it up by experimenting. One can push it up to this. And then there is a theorem saying that the average distance for any such subset in the plane is at most 0.718. But the maximum is not known. And it's believed to be this Rouleau triangle which realizes this maximum. So I would like to finish here. Thank you very much for your attention.